This poster addresses a part of the effort to determine how to treat terrestrial material and reduce contaminant levels so that it approximates lunar regolith. The application of pre-treated lunar regolith simulant materials is to utilize microwave for lunar regolith construction purposes. In the second slide, the approach addressed here is to examine the effects of a combined thermal and vacuum treatment on two lunar regolith simulants. In the third slide, a table showing various lunar regolith simulants that have been prepared, two of which, JSC1A and NU-LHT, we have examined to a limited degree. In the fourth slide, the process we followed is described. Approximately 20 grams of simulant is placed in a quartz tube, it's 12 millimeters ID, which is subsequently placed in a radiant heated furnace and attached to a vacuum system capable of 10 to the minus 5 torr. While under continuous vacuum, the material is heated at a 2.5 degree centigrade per minute rate to an elevated temperature, while simultaneously monitoring volatiles produced over the course of heating. Pressure variations were monitored to correlate with time, temperature, and volatile species during the test period. In slide 5, the experimental setup is shown, illustrating the integration of furnace, vacuum, and mass spectrometer used to detect volatiles produced in real time. A liquid nitrogen trap was used to capture condensable vapors generated. In slide 6, a temperature pressure profile generated during the heating process of JSC1A as it was heated to 1200 degrees centigrade is shown. While the temperature rise is linear, the pressure variations due to the release of various volatile species were monitored. The arrows show specific locations where the volatile species detected by the mass spectrometer were measured and are shown on the next slide, slide 7. On slide 7, the relative release of the major volatile species, water, carbon dioxide, and sulfur dioxide, are shown as a function of time over which the JSC1A temperature was rising. At the 20-minute mark, at a temperature less than 100 degrees centigrade, minor amounts of water and carbon dioxide were detected, while after 2 hours, at a temperature of approximately 350 degrees centigrade, both levels have increased. After another hour approaching 500 degrees, the water and carbon dioxide levels have increased substantially, while some sulfur dioxide is beginning to be detected. After 6 hours of heating, and approximately at 900 degrees centigrade, the levels of water and carbon dioxide have decreased noticeably, while sulfur dioxide content has increased. This relationship continued to temperatures over 1,000 degrees centigrade. In slide 8, the comparison between two different simulants, JSC1A and NU-LHT2M, heated to a 900 degrees centigrade limit, are shown. The generation of volatile material with respect to temperature is comparable, but the quantity and extent relative to higher temperature are not. In slide 9, the change in sulfur dioxide, more prominent than with JSC1A, can be seen from the NU-LHT2M with respect to time, where the blue line corresponds to 500 degrees and the orange line with 750 degrees. In summary, heating terrestrial lunar regolith simulants under vacuum will drive off volatile species not associated with lunar material and is a means of removing them. Although this approach suggests removal of water and carbon dioxide volatiles is relatively successful at temperatures below 800 to 900 degrees centigrade, sulfur dioxide removal from material that's contained in the simulant appears to require temperatures that are much higher. This information will be helpful in determining a pretreatment protocol that can be more broadly applied in preparing material for microwave sintering processes.